we do need to talk about another type of integral. All the integrals we've done so far have all been definite integrals. They cover a particular space. They go from A to B. Okay? They have bounds on them. Those are definite integrals. You can get a specific numerical answer for them. We are going to start working with indefinite integrals today. An indefinite integral is basically an integral without bounds. You solve them by coming up with the antiderivative plus c. Okay, that's really what you do. You solve the integral, figure out what the integral is, just as if you had bounds, only instead of plugging in the values, you put a plus c instead. That's it. Indefinite integrals are like taking the derivative of an equation. It is a general integral rather than a specific one. When you take the derivative at a point, you get a specific value. When you take the derivative of an equation, you get the general derivative. You get the general rate of change. We're going to be solving them, looking for the general antiderivative, looking for the general solution for the integral. Okay? Now, that being said, we're going to start doing substitution method. Antiderivatives and substitution are not interchangeable. If you are doing a problem, let's say I'm doing the integral of 3x squared plus 4x minus 5, you're just going to do straight up antiderivatives. You do not need to do substitution. However, you can't always just do a straight up antiderivative. If that doesn't work, your first attempt at solving it is to do a u-sub. Pick part of the derivative and put u in, substitute u for that part. Okay, sorry, for the integral. Now, there are some tricks to what you choose and what you don't choose. So, it's basically you have to decide your u, and then find your du from that. So you figure out what you're going to substitute in. When you look at the equation, you get some clues. For example, I have an exponential here. Okay? I have an exponential. If I have an exponential, let your u be the exponent. That's your first choice. And what we're going to do is we're going to take this integral. The integral is sine x e to the cosine x dx, and rewrite it without the x and the dx. The x's and the dx's will be gone. They will get replaced by something in terms of u instead. Okay, so we're going to replace things in here with u instead. Now, when I have an exponential, my u is generally a good choice. Would be let it be what the exponent is. The exponent here is cosine x. So if u is cosine x, I take the derivative of u equals cosine x. Derivative of u is du. The derivative of cosine x is negative sine x dx. So I'm already working on my replacements here. I now have, instead of e to the cosine x, I now have e to the u. Here, 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 they're all. Well, everybody who's here. Okay, I'll pass them out in a second. Okay. So I have replaced cosine x with u, so now I have e to the u. But I still have other stuff in here I need to get rid of. I need to specifically get rid of sine x dx. Well, I almost have sine x dx, don't I? I don't have sine x dx, but I have almost sine x dx. What do I need to do? Make it positive. Multiply both sides by -1. Negative du is equal to sine x dx. Now I can take the sine x dx and replace it with negative du. So I've taken a very complex looking integral, made it look real easy. Antiderivative of negative e to the u. negative e to the u. So this is equal to negative e to the u plus c. Now, did I begin my equation in terms of u? No, I began it in terms of x. So I need to take u and put whatever u is in terms of x back in. Negative e to the cosine x plus c. Okay, Matt. Lady. Luigi. Karen. Nick. And Byron. So yeah, that's what a u substitution is. What I take is I take something that looks really nasty. I take a portion of that equation and substitute in something simpler, take its derivative and replace it. So when I do this, notice I go from everything in terms of x dx, no more x's, no more dx's. It's all in terms of u, and then I have something very simple to work with. That's the idea. Okay, that's what a u substitution is. It's kind of like the anti-chain rule. That's the way I like to think about it. It's kind of like the anti-chain rule. Because if you take the derivative of this, the negative e to the cosine x, what do? Oh, I take this all over again times the derivative of the cosine x. The u substitution helps you do things where the original derivative would have been a chain rule problem. That's what u subs let you do. Okay? If I have something that would have been a chain rule, when I take the derivative, a u sub is a good portion of it. And we can substitute anything. Notice I didn't replace the e, I just replaced what the power of e was. I'm not replacing everything there, I'm kind of picking and choosing. And not everything necessarily gets completely replaced, but it will, and you kind of learn how to do this, okay? This is how you solve ones that you couldn't do other ways. Some of the antiderivative ones that you have when you're solving the differential equations on the first homework, this is how you can do some of those. Remember I said if you're clever, you might be able to figure it out. This will do it if you're not quite that clever, so to speak. It's the same process, though. And kids will pick this up. Oh, okay, then I got to do this. And they mentally have already figured out how that works. That's what u sub is. Okay. Let's do another example. The integral of x squared root 5 plus 2x cubed dx. Probably the most difficult part of this whole thing is deciding what your u is. That's probably the most difficult thing, deciding what your u is. And there's no hard and fast rules, but there are some good guidelines. I already gave you one of them. You have an exponential, let u be the exponent. That's a really good place to start. If you have your variable in the exponent, let u be whatever the exponent is. Okay. In this case, what do you think my u should be? What's underneath the radical? Not the radical itself, but what's underneath the radical. Okay. Let u equal 5 plus 2x cubed. Okay. Take the derivative of u. Get du. Take the derivative of 5 plus 2x cubed. You get 6x squared dx. Do I have a 6x squared? No, but I have an x squared. Divide both sides by 6 or multiply both sides by 1/6. 1/6 du is equal to x squared dx. I can now replace this, and I can replace that. So, first hint, exponents. Second hint, if you have a radical, whatever's underneath the radical. The whole thing that's underneath the radical. Okay, you can't do just part. You don't want it. You can't really do just part. You got to do the whole thing underneath the radical. You got to do the whole exponent. It can't be just part of the exponent. Okay, so this is equal to the integral of 1/6 square root of u du. You with me? Now there's some tricks to being able to take the antiderivative of this. My first trick, pull the constant out front of the integral so I can ignore it while I'm doing my antiderivative and rewrite the square root as an exponent. 1/6 the integral of u to the 1/2 du. That is a relatively simple antiderivative from there. It's 1/6 times antiderivative I subtract 1 from the power, antiderivative I add 1 to the power. So this becomes u to the 3/2. And what do I have to have in front to counterbalance that new power? 2/3. 2/3. And then because I don't have bounds, what else do I have to have? Plus c. You forget the plus c, I'm marking you wrong. That's a big one. That plus c, that's a big one. And now I can simplify it out and rewrite it in terms of x, because I don't want u, I want x. 1/6 times 2/3, 1/9. 5 plus 2x cubed to the 3/2 power plus c. There you go. I would leave it like that. I'm okay. Don't worry about giving me the goofy root, the square, and everything like that. I'm okay with it like this on this one. If you're evaluating it, you might want to think about rewriting it as a square root and cubed, because it might make it easier to do evaluations, but that's only for evaluating purposes. What's the difference if I have bounds? We'll get to that. You have to evaluate it at some point. You don't have a plus c anymore. But we'll get to that evaluation. You with me so far? It's a nice little trick. It's a nice little trick to be able to do. I'm going to tell you, I had I think it was my second year back as a college student when I returned. And I was getting my math degree, and there was a math contest, U Alpha Theta math contest. I went in, and it was a problem similar to this that none of us that took that lower level. There were 2 versions of the test depending upon where you were at. That got that question, and we wrote it down and asked one of the professors, "Oh, it's a basic U sub," and we're like, "Duh! Oh my, duh! That was stupid." I feel really good. I got 3rd place and $50 for spending an hour taking a math test, which I really love doing math tests. That was kind of cool. Well, that was because I did it for the university, and he came in on the weekends. So. Okay, pick your U. What do you think the U is going to be in this one? And this one will help some of the problems you guys have struggled with some of the other ones. What do you think it's going to be? 7x? Do you think it's going to be 7x? Yeah. Do you have an antiderivative for the cotangent? No, you don't have an antiderivative for the cotangent. See, you can't just do that. What are you going to have to do? Rewrite it in terms of sine and cosine. Because the cotangent does not have an antiderivative, you got to rewrite it. Trig functions are not nice that way. So you rewrite it as, and cotangent is cosine 7x over the sine of 7x dx. Now, this is where it gets tricky. I have choices. One works, one doesn't. Now you got a 50-50 shot. Okay. One works, one doesn't. Bingo. Sine of 7x. Let u be the sine of 7x. Here's why. If you let it be the sine of 7x, you get the cosine of x, right? If you let it be the cosine of 7x, you don't get 1 over the sine. Because remember, that's cosine over sine, which is cosine times 1 over the sine. When you take the derivative of one, you're going to have to be able to get the other. If you take the derivative of the cosine of 7x, you're not going to get 1 over the sine. You're not going to get the denominator. But if I let u be the sine of x, or sine of 7x, excuse me, my derivative is 7 cosine of 7x dx. And I don't have 7 cosine of 7x, but I can 1/7 both sides. 1/7 du equals cosine 7x dx. And now I can do my substitution. So I have the integral of 1/7 du. That substitutes for the cosine and the dx. That's my replacement for the cosine of dx. And then my sine of x, I let u be sine of x, so I get 1 over u. To make things easy, what do I want to do here? I want to pull the 1/7 out front. It actually makes it easier. Not so much the 1/7 that's a hard thing to deal with, but it makes it easier to see the antiderivative. You don't get as confused when you pull the constant out. It makes it a little clearer what your antiderivative is going to be. What is the antiderivative of 1 over u? ln of u, natural log of u. So this is 1/7 natural log absolute value of u plus c. And we have to put absolute value because we're not allowed to take the natural log of negative numbers or 0. And we have no idea what our values are going to be because it's an indefinite integral. So we have to worry about that. Okay, we can't do anything about the zeros, but we can take care of the negatives. Once again, we start in x. We need to finish in x. 1/7 natural log of the absolute value of the sine of 7x plus c. Trig ones get goofy. You will often have to change trig ones around. I believe most of the ones that you have to rework in the trig function ones, we're going to do a couple of them here today just to show you, because those are, I think, the trickiest ones, is you have to put them in terms of sine or cosine. Some of them are still a little goofy after that. Most of the ones that are really bad, they give you a hint. Like I've got a couple of them here, and I give you a hint on how to solve them. Okay, and I'll show you. So the ones that I have here today will have hints on them as well. Okay. Are you with me so far? So far we've talked about it. What do we do? And what are our choices? Our good choices are, if you have an exponential, it's the exponent. If you have a radical, it's inside the radical. If you have a fraction, it's the denominator of the fraction. Never the numerator, always the denominator fraction. Those are the first 3 things you need to think about. Okay. The other issue you would want to think about would be, and it won't work for here, but if you have anything in parentheses, let it be in the parentheses. So if you have something raised to like the 10th power, you don't want to FOIL out. If you have like x, if you have like, x, 2x squared plus 3x minus 5 squared, go ahead and FOIL it out and do the polynomial. Okay? But if you don't, higher power than that, do a U sub. Okay? And you'll kind of see what works. So this is one I was talking about with the trig one. And I'm not going to expect you to do this on a test. AP will not expect you to do this one on a test. Okay? They might do you with the cotangent, like I did. Might do you with the tangent, where you have to rewrite that in terms of sine or cosine. They were not going to do this to you because they don't expect you to have that formula memorized. I do this on homework because I think it's worth challenging you a little bit more on the homework. Build your algebra skills, build your calculus skills up by doing something a little more difficult on the homework. I would never screw you like this on a test. And I'm sorry, no. but it is a good example to get you to manipulate things. Hint, use the power reducing formula. So hint, substitute it in. Integral of 1 plus cosine 2x over 2 dx equals, and this is really ugly the way it stands. I can do this. Yeah, we can do this. We can do it the way it is. I would think that maybe pulling the 1/2 out the front first would be good, but not necessarily. There's a couple of options here. Let's talk about them before we move forward here. And there are often several ways to do this. I could put it as 1/2 plus cosine 2x over 2. Do the 1/2 separately. Then the integral of 1/2 is just 1/2 x. That's an easy one to do. You can do that and just deal with the cosine. You could take the 2, pull it out front, and make it a 1/2 times 1 plus cosine 2x. Or I could leave it like it is and just let it be, in this case, the numerator. But I got a problem with that. Okay. Cosine 2x just doesn't work. Because what's the derivative of the cosine of 2x? 2 sine 2x. Do I have a sine in there? No, I don't have a sine in there. I don't really need a sine in there. What should my u be? 2x. So 2x. Okay. So here's what I would do. Pull out the 1/2. And then I get the integral of 1 plus cosine 2x dx. Okay. And then I would do 1/2 integral of dx plus 1/2 the integral of cosine 2x dx. Because you don't have to necessarily do u sub on the whole thing. You can split this one up. What is this one here? 1/2 x dx. What's the antiderivative of dx? How many x? What do I have here in front of the dx that I don't write? 1. What's the antiderivative of 1? X. So this is 1/2. This one here all by itself is 1/2 x. Okay. But I want to do u sub for the other part. What do we say we want to let u be? 2x. If u equals 2x, du equals 2 dx. Move the 2 over to the other side, or the other side. 1/2 du equals dx. Oh, wow, this is even easier than it looks. So I have 1/2 du instead of dx. So I take 1/2 du and replace dx with that. So I have the 1/2 already out in front, and 1/2 du. And then u is 2x. So that means I have the cosine of u. What's the antiderivative of the cosine of u? Sine of u. And then what do I have with the 1/2? And the 1/2 gives me 1/4. So taking that, putting it back here in my original problem, because that, I worked this out, is my solution to this. But I started it in terms of x. I need to end in terms of x. Plus 1/4 sine 2x plus c. Not pretty. I know. The 1/2 x is the 1/2 x. I did it completely separately. Remember, you can split integrals up. You have an integral. That's what I did here. I split this into 2 integrals. Here's one integral. Here's the other integral. I solved that one that way. I solved this one using this to get that. You can split it up and do this integral, and then do this integral, and then do this integral, and then do this integral. You can do that with if it's addition and subtraction. You can split it up into separate integrals if it's addition and subtraction. Not with multiplication and division, but addition and subtraction, you can split them up. And this one I don't need to use a u sub for this part, and I can do it all by itself. But I'll do a u sub for this part over here. Okay. Pythagorean identity. I love Pythagorean identity. Sine squared plus cosine squared equals 1. Only it's not sine squared to cosine squared. Well, it is. But what's my integral of? I have an integral not of sine squared. I have an integral of sine cubed. So I'm not replacing the entire integral. I'm just replacing part of it. This is the integral of sine of x times sine squared of x dx. That's technically what I have, right? Sine times sine squared is sine cubed. So I'm going to replace the sine squared in only the sine squared portion. And you're thinking to yourself, ah, crap, that still looks bad. It does, doesn't it?
Yes.
Okay.
Yes.
So here's the tricky part. What should I let my u be? Do that. See what you get. Let u equal 1 minus cosine squared x and take the derivative. You get sine x. No, because remember, what is cosine squared? Cosine squared is actually cosine x to the second power. So if you do the derivative of cosine to the second power, bring the power down, reduce it by 1 times the derivative of the inside. The derivative of cosine squared is 2 cosine x negative sine x. No. If you do the derivative of the cosine squared, bring the power down. So you get 2. Reduce the power by 1. So you get 2 cosine x times the derivative of cosine x, which is negative sine x. So you get negative 2 cosine x sine x. I don't have man anywhere near there. Do not multiply it out. Nope. You want a hint?
Oh, just one.
Just one of them.
What? This is Matt.
Do it. Trust me. Do it. What's du? Sine x dx. Actually, it's negative sine x dx, right? The derivative of the cosine. You're not doing anti, you're doing derivatives. Take the derivative. Du equals negative sine x dx. Well, I don't have a negative sine x dx. I have a positive sine x dx. I can take this and replace that with du. The sine x dx goes away, and I've got du. Got a negative du technically. And what did I replace here? I let u be cosine. So what I have now is negative 1 minus u squared du. And tell me you can't do the antiderivative for that one. It is a lot easier, isn't it, when you do that? It's not always easy to see what you're going to substitute in. And I gave you the easy ones. Exponents, inside radicals, inside parentheses, denominators. It's when you get away from those easy ones, there are 4 really easy ones to see. Inside parentheses, inside radicals, denominators, and exponents. Those are easy use subs. Oh, I had exponential. I'm going to let it be the exponent. That's an easy one. These are the ones that get nasty. Okay? That's why we're doing some nasty ones. You can kind of see, ooh, it's not always direct. Distribute the negative. Antiderivative. And then plug back in the cosine. Well, actually, sorry, I did the same thing that many of you often do. Yeah, left the integral sign in front. Oh, that kills me. Now, this does not look like if you took the derivative, you would end up getting sine cubed. But if you take in the derivative and then use the substitution that we started the whole thing with, the Pythagorean identity substitution, you will end up with sine cubed if you take the derivative. It doesn't look like it. It doesn't work. Yeah, the antiderivative, the derivative of your answer does not always look like the original problem, but can be manipulated to look like the original problem. That's what happens here. Yes. No, you won't see this on the AP test either. Trust me, I'm not going to make you do this on there. They won't make you do this either. Nothing this complicated. But once again, it's good to challenge yourselves to see what's out there, to see what to do. Sometimes they get sometimes they're a little complicated what you have to decide. And the hardest thing is figuring out your use of. If you don't know what to do, try something. If it doesn't work, try it again. If it doesn't work, try something else. Try something else. Eventually, you'll start to figure out the tricks to doing it. I did give you, like I said, the 4 easy ones. I showed you a couple of really hard ones just to balance it out. Say, hey, these are the more difficult ones. And you'll have a couple of these on your homework. I always like to put some problems on your homework that are going to be much harder than anything I will make you do on the test. Okay, does that make sense? Step it up, challenge you a little bit more. Once in a while, you'll get an extra hard home test question, but usually they're not bad. They're challenging, but not horrible. Okay, bounds. This is where things can get interesting. There are 2 options. There are 2 options when you're doing bounds. You can either ignore the bounds, do exactly what we did, and then put it back in terms of x, and use those bounds to evaluate just as you did before. But you use a u sub to figure out the antiderivative. The other way, and what I'm going to show you on this one is, you can change your bounds. You can change your bounds. Changing bounds isn't that big a deal. So I will show you changing your bounds on this one. Now, my first question to you is, what should u be? X squared minus 4. See, I told you, there's some of them that are really easy to figure out what your u is. X squared minus 4. So u equals x squared minus 4. Du equals 2x dx. Oh, look at that. That's sweet. I hit the integral of 1 over u du. Isn't that nice? Okay, now here's the problem. I got balance. I got to deal with my balance. Okay, my options. I can either put x squared minus 4 back in, or I can change my balance. Change your balance. If u is equal to x squared minus 4, when x equals 0, u equals 0 squared minus 4, or negative 4. So in terms of x, my lower bound is 0. In terms of u, my lower bound is negative 4. No. I took 0, plugged it into here. When x is 0, what's u? See, I plugged it in, 0 squared. Yeah, I pulled it out of my butt, just like the monkey I had last night when I was bouncing around my house. I pulled it out of my butt. Did you ever have this done that? So if x equals negative 1, hang on. Sorry, if x equals 1, what is u?
Negative 3.
Yeah! U equals 1 squared minus 4, which is negative 3. Negative 3. If I start in terms of x, I can change my balance. I just take whatever x is, plug it into my original substitution. That's all you do. When x is 0, u is negative 4. When x is 1, u is negative 3. Do what we did before. Put it back into terms of x, and then plug in the balance. That's it. That's the only difference. This one saves you an extra step. You do your substitutions here instead of doing it instead of back substituting everything back in. I don't need to put x back into this equation now. I am done with x's. Period. No more x's. No more x's. What's the antiderivative of 1 over u? Natural log of absolute value of u. Evaluated from negative 4 to negative 3. This is a definite integral. I have balance, no plus c. And if you had plus c, what do you have? You'd have it evaluated at negative 4 plus c, and then negative 3 plus c, and your plus c minus your plus c, they cancel each other out anyways. That's part of the reason why you don't worry about it when you have balance. So this is the natural log of absolute value of negative 3 minus the natural log of the absolute value of negative 4. And leave it like that unless you really want to pull out your calculator and figure out what the answer is. I really don't care.
Why is it absolute?
Trying to take the natural log of the negative number. It won't work. Because e times itself will never get you a negative 3. Right? The natural log of a number is what power of e gives you that number. I can never ever multiply e times itself and get negative 3. Because e is positive. That's why. If we had 0 in there, we'd be screwed. What? I skipped it. Tell you what, you want here. For you CDO people. CDO. It's like OCD, only spelled alphabetically. For people with real problems. I am, aren't I? I'm a horrible person. I try. Okay, I'm going to tell you right now, This is ugly. This is ugly. I'm going to show you this one because this is this right here is extremely close to the inverse of the derivative of the inverse secant. Okay, this is very close to the inverse secant. That's what we're trying to do here. Now, if I take a couple of things, it'll work out. My first thing to help you see what we're doing, and remember, I give you the U substitution right there. But if we do this, do that. Take 9x squared, rewrite it as 3x quantity squared. Do that. And then I'll do my U sub. U equals 3x. du equals 3 dx. Trust me on this. Okay. I'll make it 1/3 du equals dx. And then I can do my substitutions. Okay. Once again, it's a weird one. So I can go ahead and say, all right, get 1 over, this is the square root of u squared minus 1 and du, but I still have to deal with this. And I have to deal with this here. I have to deal with this and deal with that. Well, what is, if u is equal to 3x, x is equal to 1/3 u, right?
Yeah. What?
If u is equal to 3x, x is equal to 1/3 u. So this x becomes 1/3 u. Trust me. And I don't have just du here. Ooh, dx has to be what? 1/3 du. Where that 1/3 comes from. Trust me, there are things that we will do in here I don't expect you to be able to do. But I want you to see. I want you to see how to do some of these things, where some of this stuff comes from. Okay, I want you to see how it works. There are some things that I will do in here, and I do this in several classes, where I never expect the students to be able to do this. But I do want you to see this. I want to see where some of these odd things come from. There may be a homework problem like this. I don't think so. I think I actually pulled it from the homework because we're doing it here instead. But you have it in your notes to do. Okay. Okay, so I have 1 over 3, and then I have 1/3 my denominator. So I've got a 3 in the denominator and 1/3 in the denominator. What happens to my 3 and my 1/3? They cancel each other out, right? So I have the integral of 1 over u square root u squared minus 1 du. This is the derivative of the inverse secant. You look it up, look up the derivative of the inverse secant. This is the derivative of the inverse secant. So if you see this, you recognize some of these. The inverse tangent and inverse sine are ones you're going to want to. Inverse secant, you don't have to have memorized. But inverse tangent and inverse sine might be a good idea to have those derivatives memorized. This is where knowing your derivatives really well helps. And it's not too late to go back and memorize those formulas you didn't get memorized in time for the test. You thought, oh, I'll never need them again. Guess what? You do. Okay. So I end up getting the inverse secant of 3x plus c. And I think it's supposed to be the absolute value in front, right? Okay. So the caveat what we would have here is that x is always positive or something along those lines. But it's close enough for what we need here. Okay. Like I said, and I said this at the time we were doing the derivatives, you absolutely need to have all those rules for derivatives committed to memory. Not just for taking the derivatives, but all this antiderivative stuff we're doing. Okay? Oh, the derivative of the tangent is secant squared. Oh, so if I'm taking the antiderivative of secant squared, that's the tangent. Why? Because you have the rule memorized. So if you had flashcards, I'd bust them out and start working them from the other way around. What is my antiderivative? What's my antiderivative? What's my antiderivative? What's my antiderivative? Make sure you cannot just let things go because we're done with it, because we're never done with anything in here. And wait till we start doing the actual reviewing for the AP exam, and then everything we've done will come back to haunt you.